Greetings. This is presentation 2.2 on foundations. It covers chapter 2 of the Allen text. It's our second presentation of the second week. We're going to be looking at shallow and deep foundation types. We'll be looking at foundations that are specific to particular structural components such as columns or walls, different configurations that the foundations take, either slab directly on grade or a crawl space or a basement foundation, and then some deep foundation types, caissons, piers, piles, and grade beams. So the purpose of the foundation is to transmit the building loads to the rock or the soil on which they rest. In general, the requirements of the foundation are obviously that they must not fail, resulting in a building collapse. They shouldn't settle so much as to cause any damage or impair the functionality of the building, and they must be economically, technically, and practically feasible, with no adverse effects on the surrounding structures. Here's a diagram. So down here we see the foundation, we see the footings, the foundation walls, and the, I'm not sure of what type of if this is in fact a slab or probably a built-up joist, a floor made of joists. But what this image is depicting is the different types of loads that this foundation is going to carry. So there are environmental loads, rain and snow, sitting on the roof, being transmitted down through the walls to that foundation. There are live loads inside, occupancy loads and furnishings. These are not parts of the buildings, but loads that come and go. They're referred to as live loads. The foundation must also transmit those to the earth below. And then the others, wind wouldn't really pertain to the part below ground, obviously, but ground pressure, either in the form of soil or water below grade, pushing on the foundation. So different loads that the foundation needs to accommodate. Foundation settlement is a problem. So a stable building has no settlement. The first image at the top here depicts uniform settlement, and the bottom differential settlement. So uniform settlement may disrupt surfaces or damage some areas like stairs or walks. But differential settlement is the one that's probably more common and more destructive, actually. So finishes, cladding components become distorted, essentially, and that's what this image clearly depicts. Another image depicting these types of settlements. So again, here we see uniform, and it's saying that there's a the symptom or the telltale sign is that typically there are no cracks, the whole building has just lowered. Again, not particularly common, not unheard of, but not particularly common. Tipping without cracks, so here the whole building has begun leaning over, and there's no cracking because it's at least there's a uniformity to it, the way that it's kind of leaned and tilted. And then finally, this is the most common and the most destructive, is where just one piece of the soil below will sink and allow the foundation to rest, and this is usually accompanied by cracking. You see typically running from window corners or other openings. Possible causes of these problems: number one would be the earth below. So beneath the foundation wall, the soil compresses or is washed away due to a heavy rain or a water leak. So there are numerous. Some could just be sinkholes in the earth. That's unforeseen and can't really be prevented. Other common ones, though, as it says, rain or water leak. So very inexpensive but important component to the house is the downspouts. The house collects a lot of rain up on the roof. It needs to be brought down by means of the down gutter system and downspouts. And then here, this little black extension to the downspout should be moving that water away, and at least 5-10 feet away from a house at the scale of a residential property. But this is obviously a very large hole, a big problem, but it is not uncommon to have downspouts that are just in disrepair, water that's not being led away from the property and just falling at the foot of the foundation and causing this problem. Not unheard of at all. Another is water leaks underground. Plumbing leaks are another possibility. Soil pressure causes a lot of problems. We discussed this in our previous lecture. So clay in particular is a very expansive soil. Any soil that's completely saturated with water will expand and cause a lot of pressure on the side of a foundation wall. This image here on the right kind of shows a study of an existing wall that is suffering from this problem. So they've dropped a plumb line right here. That's a perfectly vertical line, and they've measured that here at the top there's a 3 1/4 inch difference, and down at the bottom there's a 4 1/4 difference as well, and this would be from pressure coming from the soil and pushing in on the wall. So that could be tilting or bowing walls. And then design and construction defects. So either the design was faulty, something was not correct in it, or the design was correct and it just wasn't executed properly. So inadequate reinforcement, so that would be steel reinforcement within the concrete typically, which we will talk a little more about. Weak concrete, so that would be not up to where it should be in terms of what was specified probably, or the sizing of the footings was perhaps also undersized. So either in the design or the execution of it, problems could occur as well. The frost line, an important issue with foundation design. So the frost line is the depth to which groundwater in soil is expected to freeze. This depends on the area in the country that you are, the climate of that area, the heat transfer properties of the soil and adjacent materials, and if there are any nearby heat sources. So building codes account for this frost depth, and building footings typically need to be below it, so that when the ground freezes and heaves or moves, it doesn't affect the foundation. So that's what we see here. Here's a frost line, and here's a simple little pier that is, in fact, below it. This is an interesting diagram I just came across, and it's showing the effect of the actual heat loss from the building, which is a bad thing, but it's showing that it does affect the area, the earth around the footing. So in that sense, it's I guess you could say it's a positive thing, and that this foundation would be less likely to experience heaving from frost, but obviously losing heat from the interior of a building by means of the foundation is in no way a real solution to a problem. And here's a frost line map. So construction code would based on where you're located here, the building codes would dictate exactly what needs to be, what depth needs to be met. Is the top of the footing or the bottom of the footing? So here in the United States, the frost lines range from about 0 to 6 feet below the surface. Obviously 6 feet below the surface being up in the coldest parts of our country, and 0 would be down here at the very bottom where there's no frost. They don't experience frost. Here in Philadelphia, the frost line is at 36 inches. So foundations have to be dug to that depth. All right, now we're going to look at foundation types. There are 2 different types in the broadest categories or the broadest sense. They're either shallow or they're deep. Here in this diagram we see a shallow foundation on the right-hand side, and then here with some piers or caissons, a deep foundation extending much, much further down. So, shallow foundations transfer building loads to the earth very close to the base of the structure. They're less expensive and they're used whenever feasible. If it's possible, if the geotechnical engineers have determined that the earth is suitable for carrying the building, then a shallow foundation should and could and would be used. If that's not the case, and that material is not suitable in fact, then a much more expensive and much more sophisticated system would need to be designed, and this would extend downward through the layers of weak or unstable earth to reach more competent soil that is suitable for carrying the building loads. Often the choice is obvious when this soil is determined to be adequate. The choice is obvious, but sometimes it's not, and then more in-depth investigations and evaluations need to occur. Structural footings are a component that are typically used with shallow foundations. They're constructed out of brick, masonry, or concrete. They live under the base of a wall or a column, and their purpose is to distribute all of the building loads down into the earth. So down here is where we see the foundations, the footings. The footing is one component in a foundation. A common analogy is our snowshoes, where a person's weight and their foot in particular would be kind of a point load, and by putting on a snowshoe, that same exact weight is just distributed differently over the snow, and it allows a person to walk on the snow without compressing it and falling into it. And that's exactly what a footing is intended to do. It's to take all of that weight that comes down through the column and then distribute it over a greater load, over a greater area, that is. Reinforced concrete, which we will talk about later, just to mention, is will have a wire mesh or steel bars embedded in it to increase its tensile strength. We'll talk a little bit more about this as we move on, but that's what's depicted here and depicted in a number of images we're going to look at in this lecture. All of these little lines here, that's steel reinforcement inside of the concrete. All right, so now we're going to look at a couple of different footing types. These are specifically defined by the structural components that are above them. So column footings serve columns, the columns above them. Here's a basic depiction of a column footing. Here it is on the job site. We see the column here. Here's a finished column. Here's the reinforcement coming. So a second pour would be created to finish that column. And then here we see the footing below that column. Right there, buried in the earth. We only see the very top of it. And then there are several different types of footing types and that pertain to columns in particular. So simple is depicted here, just simple rectilinear pieces. Sloped footings and stepped footings provide more shear resistance. There's a tendency for this column to want to push right through that footing. The column wants to push through, and that would be a shear failure. And by kind of enhancing or building up that connection where the two meet here in the form of this pyramidal shape or this stepped kind of shape, there's more resistance to that shear or punching effect. Wall footings serve walls, obviously. So here we have a simple wall, and there's the footing below it. Here we have a concrete masonry unit wall, or CMU wall, and here we see the concrete footing below it. Here we see a wall footings that walls have not been put in place, but essentially just outlining the exterior walls of probably a small residence. And then here we see a detail of a footing. So exterior wall footing with a concrete stem. So right here, so this is a small section through the wall, the base of the wall. So here is our footing. It's given dimensions. The steel reinforcement is here, and it's called out for what it is. We'll discuss this more at a later time. Here's a small stem wall sitting on top of that footing, and then this is the exterior wall of the building. Now, this is describing the space that the footings, the foundation walls that would sit on top of a footing create, different configurations. So there are three different versions. The first is where we have the footing sitting, it might be this is a very shallow footing, so again, going back to the frost line issue, this would be in a warmer climate with the frost line right up at the top. But slab on grade can be the same even if it were in a very cold climate, and then the footing would just be extended down. A slab on grade is a slab on grade in any climate. It's just a question of how deep the footing is. Here we have a crawl space, or not a livable space, but a habitable, but a space that one could enter, and mechanical components would run through a crawl space often. So a space is created above the slab. The slab would probably be down here, and then this would be a built-up wall out of dimensional lumber, and a space is created there. And then we have a livable or habitable space when we create a basement. And this is typically a function of design and economy, really. It's not a foundation requirement that you have a basement. Actually, it's a foundation requirement that the walls are of a certain depth and a certain thickness, but it is not a foundation requirement that you create a habitable space below grade. And then here, some images. So here's a slab on grade, a massive one, commercial or industrial size. Here's a crawl space. So we're looking at an older building here with a foundation walls are made out of red brick. And here's a common residential scale basement being put in, so a habitable space down below. These appear to be utilities coming up through the slab, and these are probably tie-down straps to tie the superstructure. This would be called the substructure, and then the superstructure would sit above it. So in areas that are prone to hurricanes, you'd often find large tie-down straps securing the structure, the wooden frame probably, to the actual foundation. Another configuration is a step footing. So this is used for economy when we have our earth is on a slope, essentially. So we just need to have the footing just below the frost line. So if we pretend that it's 30 inches here, it could also be 30 inches down on this side in the front face of the building. And then it just has to follow the contours of the earth and just remain that 30 inches below. And here we see it in a three-dimensional graphic, and here we see it in the detail. So it's calling out the reinforcement as it goes, and it's telling us all of the step sizes. And it's talking about here a clear dimension, so that's how far the reinforcement needs to be from the face of the concrete. We want the steel reinforcement to be nicely buried in the concrete and not exposed and therefore prone to water infiltrating and getting to the steel and rusting it out. So that's what the cover would be. And here we just see a depiction of a simple, obviously residential scale footing, stepped footing. And as we just discussed soil types, this one is clearly has been dug out. This is probably the exact depth of the backhoe bucket, and it was just dug out. So the soil type, a clay-like soil, something very sturdy that would stand up. The soil type plus the municipality would allow, and the structural engineer, those three components really, the municipality, the structural engineer who designed it, plus the soil being as stable as it is, allows the contractor to just use the bucket for the backhoe and just dig this out. So if the structural engineer specified call it a 12-inch wide footing, probably more than that, I can't really scale here, 12 or 16 inches, the contractor, the earthwork contractor, would get a bucket that's 12 or 16 inches wide and just dig it out, and then that footing could be poured directly into the earth because the earth is stable, as opposed to having to set up forms. Spread footings. So this is just another term. This applies to both the column and the wall footings. It's just a different description. Spread footings live under columns and walls, and it's really describing what the footing is actually doing. So they're often called strip footings as well, and they're doing the same exact thing. They are the same exact thing as column or wall footings. It's just spread or strip are just different terms. And here we can see a couple. So here we have a column footing, and then here we have a wall footing with columns sitting on it, and then there's an infill wall. We'll look more at some varieties like this shortly. So just a different term for really the same thing. And I just want to look at a couple of plans quickly to see what this would look like, how the architects and engineers, probably these would be drawn by structural engineers most likely. On a residential scale, an architect may draw foundation plans. So here we see what appears to be a house, and these dark walls would be the foundation walls most likely, and the dashed lines on both sides would be the columns that are larger than them, but they are beyond sight in this plan. They're kind of out of view, so to speak, but we can see that all of these bearing walls do have footings below them. That's why we have continuous dashed lines following the dark walls. Here is a simple plan. We can see it actually here in elevation. So we have columns, and then we have column footings below them, and then we begin the structure up here. And then this image here depicts that same plan. We see the columns are the dark squares, the footings below them are the dashed areas that are larger, and then the dashed lines here would indicate something above. Those would be the beams connecting from column to column. So a simple depiction of how a column foundation configuration could look. And again, one more of the same really. It's just a little different here. We see two columns here, and then just for economy, ease of formwork, ease of pouring, just turn this into one large footing. So there would be specifications elsewhere telling us about F1, footing 1, and then here F2 and F2. So there'd be more detail, obviously, somewhere else telling us how footing F1 is created, footing F2 is created, footing F3. So we have 5 different footing types here, and details further down the line would tell us more about them. All right, moving on to deep foundations. So this is where soils directly below the building substructure are weak or unstable. Therefore, deeper foundations are needed to transmit those building loads down to deeper, more competent soils. And we see a nice depiction of that right here. So here we have firm soil right at the top, and the foundation could rest right on the very firm soil. Here, however, we have soft soil at the very top, some firm soil, and then we have to dig down deeper to get to the very firm soil that's needed. So we're going to look at a different couple of types of caissons and piles, and these are the components that would dig down deeper or reach down deeper to the adequate soil. All right, this chart, there's often some confusion between the difference between piers, caissons, and piles, and there's also some differences even within the engineering community as to how they describe it. In the Allen text, caissons are described in one manner, but then in common engineering, they're actually described a little differently. So I'm not going to read this entire chart to you, but I will kind of pick out the highlights here. So, piers, a pier is inserted down to the bedrock, so inserted being an important point, so it's not poured, but it's inserted. A caisson, by common engineering definition, is a watertight structure, and a caisson is putting a box into underwater and pouring concrete into it. So in the broader engineering world, a caisson refers to what typically happens in bridge construction. However, if you're only talking about residential and commercial construction, and you're looking at the Allen book, caissons do exist there as well, and then the watertight issue is not mentioned at all. So that's why I have these 3 asterisks up here, and then I put in this footnote. This is a common engineering definition of a caisson provided here. In the Allen text, however, and our general, general building construction, caissons are not described as watertight structures and are poured in place rather than sunken into the ground. So the definition on this slide typically applies to bridge construction. So if you dig deeper and look at caissons, you're going to find some, I wouldn't go so far as to say conflicting information, but varying definitions. So in the broader engineering world, caissons are watertight structures that are used with bridges, but for us, they are, that's not, the water tightness doesn't really pertain. And we'll look at more images and discuss more what they are, in fact. And then piles here, so that's a column that is driven. So if there's a pile driver, something forces a pile down into the earth. So here we have driven, and here we have inserted. Okay, we'll move on and look at some specific images of each. All right, so starting with caissons. So Per the Allen text, concrete cylinders poured into drilled holes. So first the hole is drilled, and then the rebar is dropped in, and then the concrete follows. That's what's happening on these two images on the right here. So in building construction, steel reinforcements being lowered into a drilled hole. Once the reinforcements correctly positioned, the concrete will follow. So in the building world, this is what a caisson is. In the bridge building world, here we have, this is a caisson. So they're building this watertight chamber in a river to become a foundation for a bridge. So just same word, just a different use, depending on the structure, actually. Okay, so now onto piles. So more slender than a caisson and are forcibly driven into the earth rather than drilled and poured. So they can be made out of steel, wood, or precast concrete, and they have a pile driver. So a wooden piece. So this is to say that nothing was dug. There was a machine that was brought in and hammered these in, and that's typically what would happen on beachfront properties, because you cannot dig a hole in any efficient manner in sand and not have it cave in on itself. So these posts, these wooden posts, would be driven into the earth. And that's what we see here. Here's the crane. The template is to guide guide the pile down, essentially. There's the pile right there, and then a cushion at the top of it, and then the hammer drops and drives the pile forcibly into the earth. Here are some concrete piles awaiting placement. So in general, there are three different ways to classify or describe piles: based on the material that they're made out of, based on the method of construction or installation. So they could be driven, which is what we just saw images of, a pile driver that forces it down. They could be bored, so it could be like an auger could pull out the earth and make way for it, and we'll see images of that. And then over here on the right, so we have driven ones that are precast. So that's the pile is actually precast. It's made elsewhere and brought in. We could also drive a pile sleeve down and then cast something in place. And we could do the same with boring piles as well. And then the third manner in which we classify a pile is how they transfer those building loads down into the earth. So they could be end-bearing, meaning the loads are transmitted right down to the very bottom of the pile, or it can be done through friction. Yes, those would be the big two, really. And we'll move on. And here, deep foundation. So piles with grade beams. So this is another structural component that is often used in conjunction with piles. So here in this image, we see the piles that are reaching down into the earth, and then a grade beam up at the top connects them, and that's what the wall would sit on. So a grade beam or a grade beam footing is a component of the building's foundation, consists of a reinforced concrete beam, that's what's right there, transmit loads from the wall above down into the pile. So the loads come down through the wall into the, here even in the middle, it comes down the wall into the grade beam and then moves horizontally until it finds the pile and then comes down. Grade beams span between piles. That's right here. That's the area that's spanning between those piles. Here's a grade beam waiting to be poured. And here's the detail of a grade beam. So here's the concrete grade beam. Here's the reinforcement in black, reinforcement that's been embedded into the grade beam and that is extended above the grade beam and connected to the slab. So here we have walls sitting directly on grade beams. Here we have a slab sitting on a grade beam. All right, onto piles. So piles are long, slender columns in the ground that transmit the loads to lower depths than where they can be carried. So this again pertains to bridges, but these same configurations exist in buildings. So here we have a pile footing. So right there's the footing. A pedestal pier. So just as similar to a footing, just up above above the surface of the earth, below the water there. Drilled, that's indicated with the 2 dashed lines, so the outermost lines would indicate that the drilling happened and then the pile was inserted, or just driven without being drilled. And then here's a spread footing, so similar to the spread footings that we saw in an earlier slide. So no pile involved there. All right, going through the different types of driven piles. Manufactured concrete or steel piles are driven into the ground like massive nails driven into a timber. So that's what we have here. Here's the massive hammer or the weight, just forcibly pushing this thing down into the earth. That's what would be happening here as well. You see the pointed pile and the pile driver with the weight at the top pushing it down. So that's a driven pile. Driven cast in situ piles. So driven, again, means it's forcibly put down. However, this is cast in situ, means in place. So it's cast in place. So a steel tube with a closed end is hammered into the earth and then filled with concrete. So that's what we see here. The hammer is pushing the thin shell down. It has completed the hole. Then they take out the thin steel shell. The reinforcement is placed and the concrete follows. So that's driven, cast in place pile. So it's the sleeve of the concrete that it's an empty sleeve, a cylinder that's driven into the earth. This is again another variation on the same. Here we see the sleeve being pushed into the earth, followed by the reinforcement. Oh, this different version here, the sleeve is being pulled out after the fact. So sleeve is in, reinforcement follows, concrete follows, and then the sleeve is taken out. That's what we see happening there, and that's the same we see here. Here, sleeve is being driven down, reinforcement, concrete, sleeve is extracted. And then bored and cast in place. So here a hole is drilled into the earth. So rather than hammered, it's drilled. And we have an auger type drill digging down into the earth. And then here we see the finished piece, the reinforcement below. And then at the bottom there's this bell-shaped piece. There's a special tool that is brought down and kind of fans out and cuts that, again, for just a greater distribution of the load, the building loads, so that there's more surface area down here on the bottom. All right, the choice of pile depends on the ground conditions and the soil strata. So if there's bedrock within reach, the piles can be driven or cast so that the loads are taken directly onto the rock. These are known as end-bearing piles. That's what we see here. Board piles are usually end-bearing and sometimes with quite large diameters. So if there's suitable stone, bedrock right here, we could just rest right on it and the load would be transmitted directly from the bottom of the pile directly into that bedrock. Version 2 is over here, the friction pile. So, however, if there's no bedrock nearby, then we need to find, we can't just bear on the end of it. So the piles are designed to transmit the load to the ground through friction between the surface of the pile and the ground. So that's what all of these arrows indicate, that it's friction from the sides, on the sides of it, that actually transmit the loads and keep the pile where it needs to be. Driven piles could be either end-bearing or friction, or a combination of the two. And here's where we again see the bell configuration at the bottom of the pile. So it's just one final slide on piles. In a structural engineering class that I teach, I delve into bridges pretty deeply. I find them to be fascinating structures. And so I just want to point out that piles can function in two different manners. So in a building over here, well, let's first just talk about the two different forces. So compression is when we have two forces that are pushing in on an object, and tension is when we have two forces that are pulling the object in two different directions. So a rope or a cable only carries load in tension. Columns carry load in compression. The earth pushes down on the column, and the column pushes back up. If we're having a tug of war, team 1 pulls in this direction, team 2 pulls in this direction, and the rope is in tension. So a tension pile is different from a compressive pile. Here's a compressive pile, which is what we typically find in a building. The structure of the building is weighing down on the pile, and the earth is pushing back up on the pile. A tension pile is the opposite, where something is pulling up on the pile, and it is friction that would be keeping this pile pulling back and resisting it. So for bridges specifically, in a draped cable or suspension bridge, we have a huge cable draping over here. There's an incredible amount of tension in that, and it is the anchorage and piles right here that would pull that cable into the earth and hold it there through friction. So a tension pile is used to transmit a pull-out force similar to that of an anchor. So a pile functioning kind of like an anchor, not being bared upon, but pulling actually. So not a application for buildings. Yes, and that is that. Okay, and then just a couple of slides. The job site I was on recently took a couple of foundation pictures. Just want to point out a few things that we see. So here the footing is coming, exterior wall footing. We just talked about soils and the angle of repose. So this is not a particularly stable soil, so we have a very great incline to this. There's a lot of rubble in it, so maybe rock had to be blasted out. So one issue we talked about when it came to soils was what's required to happen now that we have this littered with what appears to be fragments of rocks. Does it need to be cleaned out and screened, or is it suitable to be used the way it is? A question the earthwork contractor wants to know beforehand. So rock has been blasted, the soil embankment has been pulled back to a safe and stable incline so people could work safely, and now the footings are coming in place. We see the vertical rebar coming up. All these little orange pieces would be for safety issues, so no one ever fell and got impaled by a piece of rebar. That's a OSHA requirement. And all of those vertical reinforcements will tie into a concrete wall, which follows. Here we see some horizontal reinforcements. So, and here we see the formwork. So at this point they stop the pour and they're going to commence again here. So similar to these vertical reinforcement, the horizontal ones, the structural engineer will specify exactly how far they need to extend into the next footing pour, or exactly how far they need to extend up into that wall. So we see the footing in progress here. This is just a simple image of utilities have been put underground by the earthwork contractor or the utility contractors. Here, another look at the footing, and then here we see the base plate for a column that is going to has yet to arrive, and then we see that the footing has been extended. So this is where a lot of weight from the building will be coming down, and the engineer specified a larger footing at that location. Here, a nice looking foundation wall. Again, we see the vertical reinforcement, and here we see a ledge, often called a brick ledge. I don't know exactly what was to follow here, but something would be something would rest on this. Often a brick veneer or a stone, or not a veneer, but an actual brick wall would rest there. Some type of a structure is being set up to live on that ledge. And then finally, a stepped footing here, as we just discussed, and I just wanted to point out right here, this is called a key joint inside of a footing. So a key joint on the footing of the surface is used to eliminate a flat shear plane across the entire wall thickness. So the key is supposed to help transfer the shear across that joint. So essentially, we don't want that wall moving left and right, especially when we have the soil pushing in on it. So this little key joint will help prevent that. Not a very common detail. I haven't seen it a lot, but it's out there. This particular image of it I found from company advertising a barrier here, some sort of a moisture barrier, pointing out how a joint like this, concrete, is prone to kind of wick moisture, which means kind of pull moisture through it. So they were advertising this kind of moisture barrier to help prevent that kind of a wicking. And here it just points out that this block out is what they would call that key. A contractor would call it a block out. So typically formed by placing a 2x4 board inside the fresh concrete. So this concrete would have been poured, and then a 2x board cut with bevels would be just placed in there, and that's what would form that negative void there, the key. And that is all for this presentation. Thank you, and I hope you enjoyed it.